So we're starting today and we're going to explore a different type of function before. Not a polynomial, not a rational, but one that's called exponential, okay? So there's some exponent rules that you will have to recall from algebra, okay? It's often the case that if you don't use them, you have probably forgotten how they work, okay? So page 17 and page 23 in your textbooks should outline these basic rules, okay? What they tell you is how exponents will simplify, okay? If I have multiplication and I have the same base but different exponents, I can add the exponents. If I change multiplication to division, I need to change addition to subtraction of exponents. If I'm multiplying an exponent to another exponent, okay, so this is actually exponent to exponent, then I can multiply to simplify. If I'm adding, they do not simplify. So the reason for that is, like if I have x squared plus x cubed, those are not like terms. I cannot combine them. It does not get any simpler. So this one's not really a rule, but it's just a reminder that if they're not like terms, I cannot combine them with addition. With multiplication, I could. X to the 0 is just 1. The reason for that is it looks exactly like this term. If the m and the n are the same, they cancel and become 1. And if the m and the n are the same, the exponent is 0. So it's really just an application of a previous rule. A negative exponent means that this term, this factor, can be put in the denominator and become positive, okay? And a fractional exponent is a root. So like a 1/2 exponent is a square root of x, okay? You will definitely be using these often. Please make sure you review them or just put them on some note cards, have them somewhere handy so you can kind of learn them throughout the week, and that you can be an expert on these by the time you actually have to take the test, okay? But the topic for today is not on exponent rules. It's on functions that involve exponents, okay? So I want to remind us of something we've done before, and then we'll kind of build off of it. Something we've done before is looked at when an 8-pound baby grows linearly. At a rate of, let's say, 10 pounds a year. Then we could capture this with a linear function, with a function that's a line. So we had something like W for weight equals, well, which one of these things is our slope? Rate of change is slope, so our slope is 10. Our input is t, we're dealing with time in years. And then our y-intercept, it's not just the other number floating around, but it's the other number that would be sort of the initial value. And because I'm talking about it being a baby, we can picture it having just been born, that's the initial value, okay? If I had said a 1-year-old child, that would not be the y-intercept because 1 year is not the initial starting point of someone's lifetime. But this is, okay. And in this case, I would get like a visual that would be a line with a slope of 10 and a y-intercept of 8. But not all rates of growth are going to be linear. Okay, so we've already done this one. How is that going to be related to what we are talking about now? So suppose instead that we start with a pair of rabbits. Maybe you've heard the phrase about like, oh, multiplying like rabbits. Their growth is not linear, okay, but exponential instead, okay? And they create a family that doubles in size every year. Okay, so let's look at what this might be just as a t-chart, okay? So initially, so when time is 0, we have 2 rabbits. We start with a pair of rabbits. So I'm going to have input t, output r for number of rabbits. After 1 year, well, every year they get to double in size, so 2 becomes 4. After 2 years, now there's doubling, 4 becomes 8. After 3 years, double 8 to 16. After 4, double to 32. I think we understand the pattern. Let's look at this as a visual. Okay, so when t is 0, rabbits are 2. And then when t is 1, we have rabbits are 4. So 1, 2, 3, 4. Put a dot right there. Okay, keep going with our dots. When t is 2, I need to have a dot up at 8. Ooh, I'm going to be kind of into our words. That's okay. We're just trying to visualize. 5, 6, 7. Ooh, right there. All right. If I connect these, they will not be a line. If I try to make a line, I can't hit this point. If I try to make a line through here, I'm not going to hit that point. These are not in a line. These are on an exponential curve that looks like the following. Okay, there's more happening here that I can't visualize because I'm talking about like a real quantity. Okay, what that means is there's a relationship maybe that would apply for the negatives, but that relationship doesn't work when I'm talking about like rabbits. I'm not going to have a negative number of rabbits, but I do want to have some sort of an equation for what's going on here. No, I guess I call this R. So I'll say R equals what? Okay, so think about where maybe we've seen this pattern before. 2, 4, 8, 16, 32. Okay, well 2 is like 2 to the first, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the fourth, 32 is 2 to the fifth. Okay, so I need to somehow relate the thing that's changing here, the exponent, the 1, 2, 3, 4, 5, to the input. Okay, so if I notice what's going on, the exponent is always 1 more than the input. I'm just looking for a pattern here. Okay, the exponent 2, 1 more than the input 1. So I needed this function where the input plus 1 is the exponent. So for instance, for year 3, I used an exponent of 4. So this is an example of an exponential function because we have exponential growth. Okay, this is just the first example, and we'll talk about some properties and maybe the formal definition next. Okay, so an exponential function is one of the form f of x equals a to the x. Okay, so and in this instance a has to be positive. The problem with a being negative is if I start having fraction exponents but I had a negative value here, then I'm working with complex numbers, and in this class we're sticking just to real numbers. Okay, so that's our form, but let's talk about some more properties. If a is more than 1, so it always has to be positive, but if it's indeed more than 1, then I get the kind of shape of the rabbit growth that way. But in the other direction, I actually end up with a horizontal asymptote. I end up with a function that's getting closer and closer to the x-axis. Okay, this is for a greater than 1, and we would call this growth. If the a is less than 1, okay, still positive but less than 1, so maybe this a value is now a fraction, a half, a third, 2/5, something like that, then I have the opposite effect. I have what we usually call decay. Okay, both of these graphs have a lot of similar properties. We're going to talk about their domain, their range, their intercepts, both the x, the y, and any asymptotes. All right, so the same things we've been talking about when we talk about a lot of our functions. Okay, so looking at the visuals, domain is the x. So squish the graph down to the x-axis. What gets covered? Everything. Negative infinity to infinity. But now if we squish it into the y-axis, not everything gets covered. The graph only lies above 0. Okay, so I'm only getting, if I squish it in, I'm only getting 0 to infinity covered. not including 0. If I squish this in, I'm still not hitting 0. X-intercept, where do we cross the x-axis? I don't. None. Does not exist, maybe, I think is the pretty common term that you've been plugging into WebAssign, DNE. The y-intercept, okay, so for this, not obvious on the graph, but if I plug in y-intercepts occur when x is 0. So I'm talking about what is any number to the 0 power. Any number to the 0 power is 1. So both of these have a y-intercept of 1. Okay, so I can just add that to my graph. Horizontal asymptote I already mentioned, but let me just remind us what's going on here. What is the graph approaching either as it goes off to positive infinity or negative infinity? Well, to positive infinity, it doesn't approach anything. It just gets bigger, bigger, bigger. But when it goes off to negative infinity, it's actually getting closer to the x-axis, which is the horizontal line, y equals 0. This graph approaches it in the other direction. As I take this graph to the right, my values get smaller and smaller and smaller. They're all approaching 0. Vertical asymptote does not exist. I'm not approaching any vertical line. I get bigger, 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 bigger without boundary. If there's no boundary, there's no vertical asymptote there. Okay? Exponential functions are useful not just to categorize certain types of growth of populations, but also growth of money. Okay, so business majors, or if you have a bank account, or if you have student loans, you're going to have to deal with something exponential. Okay, that comes up when you talk about compound interest. Okay, compound interest is like if you deposit your money in a bank. Let's talk about positive, like you're growing your money. Okay, you put your money in the bank, and then at the end of a certain term, the bank gives you some interest, but it puts that interest directly into your account. So the next term, not only do you have your original money, but now you've got your interest, and you get interest on that, and then that gets deposited in, and now you've got original money, first term interest, second term interest, and you get to grow interest on that whole bundle. So you're growing that money actually exponentially, which you should like, because think about what that curve looked like. Nice and big, right? So compound interest is your friend if you have money that you put in a bank, and it's not your friend if you're taking out loans, because what it means is you keep having to owe more and more. It's very, seems unfair, okay? So compound interest grows according to this function. Okay, so I'm outlining it the same way you would maybe see it in a business class. And we'll go through what each of these variables means to us. Okay, so P is called principal. And, spelling this right? Okay, principal, it's your starting amount. All right. 1 is just 1, R. R is an interest rate. Just make sure when you have R, it's always as a decimal. So if we talk about 2%, you got to convert that to 0.02. Otherwise, your whole formula will be off. T, I'm just going to say is time in years. N is the number of compounding terms in a year. Okay, so you may hear the phrase compounded semi-annually. That's twice a year. Like the semi-annual sales happen twice a year. If it says quarterly, okay, that means 4 times a year. If it says monthly, then your N is 12 because there's 12 months. If it says compounded daily, then you can use 365, maybe 365 and a quarter. I don't know what they do for the leap years. A then is the accrued amount. Accrued just means the end, how much money you have at the end of your time period. Okay, so we have all of these variables that we'll have to account for when we're given a compound interest problem, which is what we're going to do next. All right, so I want to leave the formula up here, but hopefully you've recorded all this important information. So I'm actually going to do like a compare-contrast thing. If we start with two options here, option one is you start with just $100, and maybe you receive the $10 a year from, you know, an aunt, a grandma, someone gives you $10 every year. Maybe around your birthday or something like that. And all you do is you keep that money under your mattress, or you tuck it away in your wallet. You don't put it in a bank. You don't get any interest on it. So you just keep the money in a safe place, okay, but not a bank. All right, this is an example of linear growth, okay? $10 every year. That means your slope is 10, that's your rate of change, and your input is t time, okay? You started with 100. That's your initial value, that's your y-intercept. So this one is not an exponential function. I didn't talk about compounding, but I'm going to use a for accrued amount equals 10t plus 100, okay? That is linear. Here's an alternative situation. Maybe you invest that initial $100 in an account that earns 8% interest. That's pretty much unheard of nowadays. Okay, most accounts are earning 1% or less, but this problem's not interesting if I plug in 1, so let's pretend that there's a bank account out there where you get 8% interest, compounded monthly. Okay, so 8% interest, that means rate as a decimal is 0.08. If I'm investing $100, that's my initial amount, that's my principal, that's my starting value, my P. Compounded monthly tells me N is 12. There are 12 months, N is the number of terms, N is 12 here. So in this situation, I'm going to plug in everything we knew, excuse me, and say A is 100 times the quantity 1 plus 0.08 over 12 raised to the 12t. Okay. Now in both of these situations, I want to ask, which one's better, right? Which one would I rather do? Okay, so you can come to your own conclusion right now, and then we'll talk about what that answer might be. And it might be sometimes this one's better, but sometimes that one's better, depending on your needs. All right, so I'm going to draw just a really rough sketch, okay, really rough because I don't have a ton of board space, and we're going to talk about lots and lots of years. This one's a line. That's really the only rough thing I need to know. Starts at 100, grows linearly. Okay, like I said, rough sketch. This one's exponential, but the principal, the starting amount is still 100. So it's going to have a dot at 100. And then what is it going to look like? It's actually going to look like this. Right, it looks like our exponential function model. It looks like the rabbit growth problem, okay? What's happening here is I want to determine what this point is. Because sometimes it's actually better just to keep the money underneath your mattress and do nothing. Only for a certain point. After that point, look at which function's on top now. The exponential one, and this one becomes the better bet, okay? I'm not going to work out the algebra because the algebra here is actually harder than what you would have to do on a test or quiz at this point. And I will just tell you, if you were to graph this in Desmos and just ask Desmos, where do these intersect? Desmos would tell you 48.8-ish. All right, so this is rounded. So that's the number of years it would take for these two curves to coincide, okay? About 48 years. So that seems like a lot, but what's happening here is that at first this is better, but then this takes over, and this will always be better in the long term, okay? So thinking about exponential growth is it's always going to overtake linear growth. It's just a question of how long you have to wait, okay? All right, again, just really want to highlight how important these are going to be. You can start reviewing them, make sure you're comfortable with them, make sure you can apply them to the different problems that you're seeing.